Hello everyone, welcome back to Abstract Algebra. Today we're going to take a little break and review things we have seen. So I'm going to do some examples through the quaternions. Remember that I already, a while back, I already took a break and explained things we had seen, concepts through the quaternions. So we're going to do that again today. So let's do that. So remember that we have seen the quaternions, and I'll remind you in a second what the quaternions are. But the quaternions have a subgroup, which is plus or minus one. So what I want to do today is try to understand what is this quotient group. What is the structure of this quotient group? Now, the first thing to prove is that this is in fact a normal subgroup of Q8. So we will do that, and then we'll try to define, try to understand what is the structure, and then try to define an isomorphism, a group homomorphism, and then we'll show that it's an isomorphism also. So we'll review all the concepts we have seen. Okay, great. So let's start with the definition of Q8. Remember that Q8 is a group with 8 elements, plus minus 1, plus minus I, plus minus let me write this correctly, plus minus j plus minus k, such that the properties are that I squared is equal to j squared equals to k squared equals minus 1, and that I times j times k is minus 1. In summary, what's happening is that minus 1 acts like you would imagine. I times minus 1 is minus I, and so on. But we also have that I, j, and k. If you go in this direction, so if you multiply I by j, you get k. If you multiply j by k, j times k, then you get I, and so on. While if you go on the opposite direction, then you get the negatives. So I times j is k, but j times I is minus k. Okay, great. And then you can check that H itself is a subgroup. So how do we check that something is a subgroup? Well, remember that we have a criterion to check that something like this inside Q8 is a subgroup. So this is going to be the first thing I do. Remember that the criterion just says that for all H1 and H2 in H, we have that H1, H2 inverse is in H. So this is my general criterion for subgroup. So I can do that. First of all, notice that 1 is in H, and the inverse of 1, which is 1 itself, is in H, and minus 1 is in H, and minus 1 inverse is minus 1, which is also in H. So H is closed under inverses. And now second, any operation such as H1, if H1 and H2 are in H, then each one of those is some plus or minus 1. So H1 times H2 inverse will be something like maybe plus or minus 1 times some minus plus 1 of some sort. So this will be some plus or minus 1, which will be in H, and therefore H is a subgroup. Now let's check. We want to know about whether H is normal. So let's find all the cosets of H in Q8. So how do I check what are the cosets of H in Q8? Remember that a coset, let's do left cosets for now. So the left cosets will be GH for some G in Q8. So I have the coset that gives me the identity. So with the identity, so 1 times H, that is just H. And then if I have minus 1 times H, that is also H. Remember, if G is in H, GH is itself the coset H. Now, if I have IH, that is, remember, H itself is plus or minus 1. So if I multiply by I times 1 is I, and I get I and minus I. That is the same coset as minus I times H. And I also have K or JH first. JH will be J minus J, which is the same as minus JH. And KH will be K minus K, which is the same as minus KH. Okay, so I have actually found that I have 1, 2, 3, and 4 different cosets. And so that tells me that I can actually write Q8 as a disjoint union of cosets of H, namely H, disjoint union with IH, disjoint union with JH, disjoint union with KH, which we know from the general theory that it's something that always happens. The fact that there are exactly 4 cosets that are disjoint and cover all of Q8 tells me that the index, which is precisely this number, is 4. Okay, and we can, in fact, now verify Lagrange's theorem. Let me actually, before I move on to do that, let me do the right cosets in this case. The right cosets will be things of this form, but notice that I will again have H, and then HI will be also I minus I, because multiplying on the right 1 and minus 1 is the same as multiplying on the left 4 minus 1. If this was another coset that had I in it, it would probably not be the same thing, but in here it is. So what I'm using is the fact that I times, say, minus 1 is the same as minus 1 times I. The multiplication by minus 1 commutes with I. So I get the same as H minus I, and then I will also have Hj is the same as H minus J, and Hk is the same as H minus K. And importantly for us is the fact that these are also the same as the left cosets. Okay, so in any case, I also have a breakdown of Q8 as right cosets if you want. So it's also HI union, HJ union, HK. Great. So next, let's verify Lagrange's theorem. So now we are going to verify Lagrange's theorem for Q8 and H. So what does this mean? It means the following. Lagrange's theorem tells me that if I have a subgroup of a finite group, then the size or the order of G will be the order of H times the index of H in G. And in our case, we have that Q8 is 8, and the size of H is precisely 2, and the size of the index, we have seen that is the number of cosets, that is precisely 4 in this case, so it does match. And this is for left cosets or right cosets, I get exactly the same quantity, so that is true. Now, is H normal in Q8? Remember, what does it mean for a subgroup to be normal? We had a definition and actually 2 other equivalent statements. Let's say A, for all the G's in G, we have that the left coset is the same as the right coset, or alternatively, for every G in G, GH, G inverse is contained in H, or C, equivalently, for all the G's in G, GH, G inverse is, I meant actually this one to be the equality, and then it is equivalent actually to just one inclusion. So we can actually just check A directly in this case because we have seen that for, well, for the identity, of course, I just get H, and that is the same as the right coset. But I have also seen that the left cosets are just the right cosets in all cases. In fact, if this was plus or minus I still get that the right cosets coincide, the right cosets with J coincide with the left cosets, and the left cosets with K uh, coincide with the right cosets. So because all of this, that is for every element of G, we do get the equality of left cosets and right cosets. Yes, it is normal. Now I can also just check C quickly, because if I have any G in Q8 and H is in H, then H is plus or minus 1, and G times 1 times G inverse, that is G inverse, that is 1, and G times minus 1 times G inverse, that is also, because minus 1 times G is G times minus 1 is minus 1 times G everywhere. This will be also minus G times G inverse, because the minus 1 commutes with everything, and that is just minus 1 times 1, which is minus 1. So it works also from this definition. You have to check just that this will work for any G in Q8, but that's how multiplication by minus 1 works. So yes, it is normal. Great. So what next? Actually, before we go on to talk about the quotient of Q8 by H, since we've used several times that minus 1 commutes with everything, let's talk about the center of Q8. So recall that the center of a group are those elements that commute with everything. So these are elements of G such that GH is HG for every H in G. So what elements will commute with everything? And clearly, what we've seen is that H itself, plus or minus 1, that will commute with everything in the quaternions. So what we want to know, is there anything else that commutes with everything else? But I cannot be in the center, is not in the center, because I does not commute with J, right? This is K, but this is minus K, so it doesn't commute. J cannot be in the center for the same reason. Same reason tells me that IJ is not JI, so that cannot be in the center. And similarly, K cannot be in the center of Q8, because, for example, J times K is not the same as K times J. Therefore, there cannot be I, J or minus J, K or minus K in the center. And what this tells me is that then the center itself has to be equal to H, equal to just plus or minus 1. So we've computed the center of Q8. Great. Let's now talk about the quotient of Q8 by H. So H is normal in Q8, and therefore Q8 modulo H is a group, and I want to know what group is this. Okay, so what is Q8 modulo H? Remember that as a set is the cosets that are disjoint, so it has exactly 4 cosets, IH, JH, and KH, so it's a group of order 4. Now, we know there are 2 groups of order 4, it's either z modulo 4 or z modulo 2 cross z modulo 2, so I have to decide which one it is. And for example, I can write a Cayley table and see which one it is. So I can just write down all the elements of my group, of my quotient group, and see what happens. H times H is H, and if I multiply H by any other coset, I will get the same coset back. Remember that GH times HH is GH H, so that's what I'm doing here. Just multiply the representatives. This will also be IH, JH, KH. And now I times I is minus 1, so I get H. J times J is also minus 1, so I get H's in the diagonals, in the diagonal elements. I times J is K. But J times I is not K, it's minus K, but I actually, KH and minus KH do give me the same coset, so I do get this. So let me say that in here, that IH times JH is IJH, which is KH, and JH times IH, that is JIH, which is minus KH, but that coset is the same as KH. So I do get commutativity here, even though the original group was not commutative. Okay, so I times K, that is going to be giving me JH, K times I, that is going to give me JH, and J times K will give me the IH. Okay, so now what you see is that I have a group where every element is of order 2, so it cannot be z modulo 4 because there's no element of order 4. So I claim that this quotient is then isomorphic to z modulo 2 cross z modulo 2. And we want to prove this as an isomorphism. So let's give an isomorphism of the two. So now I want to write an isomorphism from Q8 modulo H to Z modulo 2 cross Z modulo 2. So let's write one. I'm going to just write an isomorphism that goes from Q8H to Z modulo 2 cross Z modulo 2, and it's going to send, I'm just going to write it all out. Okay, so H itself is going to be going to the identity element. IH is going to go to 1, 0. JH is going to go to 0, 1. And KH is going to go to 1, 1. Is this an isomorphism? First of all, notice that it is bijective because it is injective plus surjective, right? This has 4 elements. This has 4 elements. I get all of them, and clearly the map is injective, so it's a bijection. And now I have to also check that is respect group structure. So how does it respect group structure? You can just, you would have to see, well, we want something like psi of A star B is always psi of A star psi of B, right? Where this is in, this would be happening in Q8 modulo H, and this would be happening in Z modulo 2 cross Z modulo 2. So let me just do some examples that this is actually happening. So for example, psi of H or IH times IH, that is on one hand psi of I square H, which is psi of minus 1 H, which is just psi of H, and therefore H goes to H. Or I can just check that psi of H times psi of H, I also get, the H maps to the identity, which is 0, 0. and psi of IH goes to 1, 0, and 1, 0. If I add them together, I get 2, 0, which is congruent to 0, 0, which is the same as psi of the identity element in the quotient. So it works there. Let's just prove that it works in some other case. So for example, IH star JH, how much is that? That is psi of IJH. That is psi of KH, and K mapped to 1, 1. And on the other hand, psi of IH plus psi of JH, how much is that? IH mapped to 1, 0, JH mapped to 0, 1, and 1, 0 plus 0, 1 is 1, 1. And similarly, all psi of GH star HH is the same as psi of GH plus psi of HH. So it is an isomorphism. Uh, so psi is an isomorphism, and Q8 modulo H is isomorphic to Z modulo 2 cross Z modulo 2. So what we've seen is that Q8 modulo H is isomorphic to Z modulo 2 cross Z modulo 2. And we've sort of like constructed that isomorphism just from looking at this group and identifying that it had that structure. But you could think like maybe what's happening is that there is some map from Q8 to Z modulo 2 cross Z modulo 2 such that maybe there is some other map, say phi, such that the kernel of phi is precisely plus or minus 1. And you could think that maybe because, well, if minus 1 is going to be in the kernel, maybe it's squaring. So is that a homomorphism and it's plus or minus 1 the kernel? So let me ask that question. So let phi from Q8 to Q8 be given by x goes to x squared. And the question that I want to ask is phi a group hom, in which case the kernel is plus or minus 1, and we could try to do something about that and then prove that plus or minus 1 is normal because it is a kernel of a hom. But it turns out that this is not a group hom. So what I want to know is phi of A times B always equal to phi of A times phi of B. And well, that is in fact not true. So let's see what happens. This would be phi of AB would be AB squared. This would be A squared, and this would be B squared. So what we're asking, is this always true for all A and B in Q8? Is the square of A times B equal to the square of A squared, the square of A times the square of B? And this is not always the case. If G is commutative, we do have that AB squared, which is AB is the same as A squared B squared. But if for this to here, we're using that that something is abelian. But without that commutativity, that is not necessarily the case. And for example, if I have I times j squared, that is k squared, which is minus 1. But if I do I squared times j squared, I squared is minus 1, j squared is minus 1, and minus 1 times minus 1 is 1. So these are not equal, and therefore phi of I times j is not phi of I times phi of j, where phi of A is A squared. So phi is not group hom. So you have to be a little bit careful with what is a group hom and what isn't. Okay, the last example I want to do is the following. Let's finally just see if are there other groups that are normal, and I'm going to test the following subgroup. So let n be the subgroup generated by j, which is well, we have 1 and minus 1, and j and minus j are in that subgroup, and this is a subgroup of Q8, and I want to know, is this normal in Q8? And to do that, let's look at, first of all, what are the cosets of n? Well, the cosets of n itself is 1 minus 1, j minus j. And then there are other cosets. For example, I is not n, not h, but n. I is not in n, so this will be a new coset. If I multiply by I get I minus I times j is k, and I times minus j will be minus k. And those are all. So that tells me that Q8 is actually this joint union of n and in, like that. Now, if I do the right cosets, I have n, and let's see what is n times I. N times I, so 1 times I on the right, I still get I. Minus 1 times I still get minus I. J times I, that is minus K, and minus J times K is K. So I actually get the same thing as IN. So what does this tell me? This tells me that n itself is normal, because what happens if I do gn for any g in G? Well, if G is in n, then of course gn is the same as ng, and I get what I want. And if G is not in n, then you can see what happens. For example, I just checked with I, and that gives me the same thing as ni. Or Kn, you can see that Kn will be K minus K, I, and minus I. So I get the same thing actually, that nk. And the same thing for the negatives. So minus I times n is n times minus I, and minus k times n is the same as n times minus k. So in all cases, I get an equality, and all these tells me that n is indeed normal in Q8. Now, that actually I could have known from the theory, because Q8 modulo n, it has exactly 2 elements, n and in, which, by the way, now that we know n is normal, this is a group of order 2, so this is isomorphic to Z modulo 2. But this also tells me that the index of n in Q8 is 2, and we have a theorem that tells me that any subgroup of index 2 is normal. So let G be a finite group, and H in G of index 2, so that GH is 2, then H is normal in G. Let me show you the proof. So let G be in G. First of all, if G is in H, then automatically GH is the same as H is the same as HG, and we get what I want. So suppose G is not in H. If G is not in H, then GH is not H, and since the index is 2, we get that Q8 is H, this joint union with GH, because that is the definition of index. There's going to be two cosets that are disjoint, and I already found one that is not H, so I have exactly two, so that is true. But also, the right coset will not be the same, so I also get that Q8 is H disjoint union HG. And now if you compare the sets, since H is equal to H and these are disjoint unions, what I must have is that the left coset is actually the same as the right coset, because I have a disjoint union of Q8 as H times H union something, H union something, and those two things have to be exactly the same. The complements have to be the same, because this says in both ways that GH is Q8 minus H, and the second line says that this is also HG. But if this happens then for all G in G, that implies that H is normal in G, which is what I wanted to prove. So now we see that this fact alone tells me that N is a subgroup of Q8 that will be normal. So Q8 has a normal subgroup N, and now we see that in fact plus or minus 1 is normal in Q8, as we've proved at the beginning. The subgroup generated by J, I just proved that is normal in Q8. But the subgroup generated by I, or the subgroup generated by K, those are also normal in Q8 because these are also of index 2. Okay. This was normal, in fact, because plus or minus 1 is the center in Q8, because plus or minus 1 is equal to the center, and the center actually is also always normal. And now, well, we also have that Q8 is normal in Q8. And if you remember, these are actually all the groups, all the subgroups of Q8 are precisely these. So all subgroups of Q8 are normal in Q8 without Q8 being abelian. Remember that if you have a group that is abelian, every subgroup is normal. But just because all the subgroups are normal, that doesn't mean that the group itself is abelian. Okay, so this is an example of a group where all the subgroups are normal for some reason or another. Okay, so we'll stop there for the time being.